Good morning, students. Welcome you all for next generation learning. Today we are going to see the subject physics, class 10, chapter number 13, magnetic effect of electric current. Topics: magnetic field due to a current through a circular loop, magnetic field due to a current in a solenoid, electromagnet. Recapitulation of last class. This is a bar magnet. Around a bar magnet, see the magnetic field. The magnetic field lines are closed loop. And see, the direction of the magnetic field is in outside of the magnet, north to south. For inside of the magnet, south to north, it is discovered by using the magnetic compass. The next, magnetic field due to a straight current carrying conductor. So the magnetic field around a straight current carrying conductor or concentric circles. See, it shows concentric circles. And the direction of the magnetic field around a straight conductor is identified by using right hand thumb rule. The thumb represents the current direction. The curved fingers represent magnetic field direction. And the last class I discussed there are the three type of conductors. One is straight conductor, circular loop and solenoid. What is the difference between the circular loop and solenoid? The circular loop has only one turn. In only one turn means that is circular loop. The solenoid has more number of turns. When the number of turns are increased, that is called solenoid. So this is the difference between the circular loop and solenoid. The next today's topic, magnetic field due to a current through a circular loop. Suppose the straight wire is bent in the form of circular loop. See, this is a straight wire. If we bend the straight wire, we get circular loop. So the current is passed it. See here, the current is passed in the circular loop. How would the magnetic field lines looks? See, this is a magnetic field lines around a circular loop. How would the magnetic field lines looks like? We know that the magnetic field produced by a straight current carrying conductor depends inversely on the distance from it. So here the magnetic field, so this is a magnetic field around a straight conductor. It depends on the distance. That means the magnetic field strength is inversely proportional to the strength. What is the meaning of that? The magnetic field strength is inversely proportional to the distance. That means, see here, this is a magnetic field around a straight conductor. When the distance is increased, the strength of the magnetic field is decreased. See, the first two circles are closed. When the circles are increased, when the distance is increased, the strength of the magnetic field also decreased. Similarly, at every point of a current carrying circular loop, this is a current carrying circular loop. So the current is passed through the circular loop. The concentric circle represent the magnetic field around it. So these concentric circles are represent the magnetic field around it, around the circular loop. And it would become larger and larger as we move away from the wire. And see here, this magnetic field are larger and larger when the distance is increased. By the time we reach at the center of the circular loop, this is the center of the circular. See, this is a circular loop. At the center of the circle, this is the center of the circle. By the time we reach at the center of the circular loop, the arc of these big circles would appear as a straight line. And it is clearly shown in this image. See, at the center of the circular loop, the magnetic field line is straight line. That means in the arc became straight when it reached at the center. So how do you find the magnetic field direction around a circular loop? See, here the circular loop is getting from the straight conductor. So this arc is act as a one straight conductor and this arc act as another straight conductor. And see, the current is flowing in the circular loop. So the current direction is enter in this direction and leave out from this direction. So here the current is upward and here the current is downward. You know that how to find the magnetic field direction around a straight conductor. Using right hand thumb rule, we can find the magnetic field direction around a straight conductor. So first we will find for this side, this circular loop as I drawn the straight. Current is positive, so the upward direction. So see here, the current is upward direction. Hold the conductor in your right hand. The thumb represent current direction. The curl finger represent magnetic field direction. So when the current is upward, the magnetic field is anti-clockwise. And it is shown here, the arrow mark. See here, the anti-clockwise. So in each curve you have to mark the arrow mark. For this conductor, this curve acts as a one straight conductor. Here the current is downward direction. So see, this is a downward. Hold the conductor in right hand. The thumb represent current direction. The curl finger represent magnetic field direction. So when the current is downward, the magnetic field direction are clockwise. So you have to mark the arrow mark in the clockwise direction. So from using right hand thumb, we can find the magnetic field direction around a circular loop. And see one of the beauty one. And inside of the circular loop, the magnetic field directions are same. When it reaches at the center, it is a straight line. I hope you understood how to find the magnetic field direction around a circular loop. and magnetic field to a current through a circular loop, we know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. In straight conductor, we know that when the current is increased, the strength of the magnetic field also increased. So from this we can say that the magnetic field is directly proportional to the current. When current increased, magnetic field also increased. When the current decreased, the magnetic field also decreased. If there is a circular coil having n turns, see this is also circular coil but it has n turns. The field produced is n times as large as that produced by a single turn. Do you understand what is the meaning of this? If you take in a single turn, it produces the magnetic field at each and every point. If the number of turns are increased means the n times the magnetic field strength also increased. This is because the current in each circular turn has the same direction and the field due to each turn then just add up. See here, this is a first turn, this is second turn, this is third turn and fourth turn and fifth turn and sixth turn. So here I took 6 turn wires. All the wires are connected to the battery, positive and negative. So in current direction for all the 6 wires for in this side is upward. For this side the current is downward. So each and every turn produce the magnetic field. So the current direction also same. So we can add all the magnetic field. So when we add all the magnetic field for 6 turns, the strength of the magnetic field is large comparing to the single turn. You have to take a rectangular cardboard. See, this is a rectangular cardboard. This is an activity. And having 2 holes, this is a holes. Insert a coil having n number of turns. This coil having n number of turns. You have to insert into the cardboard. Connect the end of the wire to the battery, key and rheostat. Here the rheostat is missed, but you have to connect. Then you have to sprinkle some iron fillings near to the circular coil. Plug the key. You have to tap the cardboard gently for few minutes. Note down the pattern of the iron fillings that emerges on the cardboard. And see this animation. This is a number of turns coil. Number of turns, it has number of turns. When the current is passing through this wire, the magnetic field is produced around it. And see the pattern of the magnetic field. They are concentric circles. And factors on which magnetic field produced at the center of a current carrying wire depends. So how to increasing the magnetic field strength around a circular loop? The one is, if you are increasing the current, the magnetic field strength also increased. So the amount of current flowing through a wire is increased means the strength of the magnetic field also increased. So we can write the strength of the magnetic field is directly proportional to the current. The next one, radius of the circular wire. The radius here, the radius is nothing but a distance. When the distance is increased, the magnetic field strength also decreased. So the strength of the magnetic field is inversely proportional to radius of circular wire. The 1 by means that is inversely proportional to. The next one, if the number of turns in a circular wire. If the number of turns in a circular wire increased means definitely the strength of the magnetic field also increased. So the strength of the magnetic field is directly proportional to the current and directly proportional to the number of turns of wire, but they inversely proportional to the distance. Here the radius is nothing but distance. So I hope you understood the magnetic field around a circular loop. The magnetic field around a circular loop is concentric circles, and the direction of the magnetic field is identified by using the same right hand thumb rule, and the magnetic field line inside the circular loop is straight line, and inside of the loop all the magnetic lines are in same direction. So this is we learnt magnetic field to a current in circular loop. The next topic is magnetic field to a solenoid. A coil of many circular turns. So a coil of many circular turns of insulated copper wire wrapped closely in the shape of cylinder is called solenoid. You have to take pencil and take any wire, just wrap around the pencil. This is called solenoid. So a coil of many circular turns of insulated copper wire wrapped closely in the shape of cylinder is called solenoid. And see, so when the current is given to the solenoid, the positive and negative. So the current is flowing in the solenoid. When the current is flowing in the solenoid, the magnetic field is produced around the solenoid. And see the pattern of the magnetic field lines around a solenoid. You have to see the pattern of the magnetic field lines around a solenoid. Now compare the pattern of the field with the magnetic field around a bar magnet. So this is a bar magnet. You have to compare the magnetic field around a bar magnet with solenoid. Do they look similar? Yes, they are similar. The magnetic field around a solenoid is same as the magnetic field around a bar magnet. In fact, one end of the solenoid behaves as a magnetic north pole and while other behaves as a south pole. How the bar magnet have the two poles north and south? The same as the magnetic field produced around a solenoid have two poles, one is north and another one is south. The positive side always south, the negative side always north. The field lines inside the solenoid are in the form of parallel straight lines. But see, for inside of the solenoid, the field lines are straight and parallel to each other. This indicates that the magnetic field is same at all the point inside the solenoid. So, when the magnetic field lines are parallel and straight line, this indicates that for inside the solenoid, the strength of the magnetic field is same at all the point. That means the field is uniform inside the solenoid. Do you understand? If you take a solenoid, the solenoid has two poles, north and the south, the same as for bar magnet. But inside of the solenoid, all the magnetic field lines are parallel and straight line. This parallel and straight line indicate that the strength of the magnetic field is same at all the point. That means the magnetic field is uniform. And the next topic is electromagnet. What is the uses of this solenoid? This solenoid is used to make a electromagnet. How? A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. The magnet so formed is called electromagnet. Do you understand? You clearly know that for inside of the solenoid, the magnetic field strength is same at all the point and also uniform. When we insert the soft iron into the solenoid, and the soft iron materials are converted into magnet. So such type of magnet are called electromagnet. Why it is called electromagnet? When we are giving the electric current to the solenoid, the magnetic field is produced around the solenoid. Due to that magnetic field, the iron material are converted into magnet. When I stopped the switch, that means if there is no current flow in the solenoid, means there is no magnetic field around the solenoid. If there is no magnetic field around the solenoid, means the soft iron never converted into magnet. So when the electric current is given, it converted into magnet. Such type of magnet are called electromagnet. It is a temporary magnet. Once we remove the current from the circuit, it does not behave as a magnet. So it is a temporary magnet. The electromagnet is a temporary magnet. See here, an electromagnet is called as a temporary magnet. Why it is temporary magnet? Once the current is stopped in the solenoid, the magnet does not behave a magnet. The iron material does not behave a magnet. Because electromagnet is made up of insulated copper wire wrapped soft iron, which allowed to flow in it. At that moment, iron gains its magnetic properties, and when the current is switched off, then there will be no flow of current, and hence iron loses its magnetic properties. Hence it works temporarily as long electric current flows in conductor, and hence known as temporary magnet. So you take one soft iron and also take a conductor, wrap the conductor wire around the soft iron, then give current to this wire. When the current is flowing in the number of turns, it behaves as a solenoid, and for inside of this we kept the soft iron. So this soft iron gains the magnetic field from the solenoid and changed into magnet. Once the current is off, if there is no current flow in the solenoid, if there is no magnetic field around the solenoid, means the soft iron does not gain any magnetic field. So such type of magnet are called electromagnet. And see the circuit diagram. The battery is connected to the solenoid, and the soft iron is inserted into the solenoid. I hope you understood the magnetic field around a solenoid and the electromagnet. What is the uses of the solenoid? The uses of the solenoid is it is used to magnetize the iron material. The homework question, the first question, draw the magnetic field lines of force due to a circular wire carrying current. In B question, what are the various ways in which the strength of the magnetic field produced by a current carrying circular coil can be increased? In second question A, what is a solenoid? Draw a sketch to show the magnetic field pattern produced by a current carrying solenoid. In B question, name the type of magnet with which the magnetic field pattern of current carrying solenoid resembles. C question, what is the shape of field lines inside a current carrying solenoid? What does the pattern of field lines inside a current carrying solenoid indicate? The third question, what is an electromagnet? Thank you for watching. If you have any doubt in this topics, you can ask through the teachment. I will explain you again. Take your science book and open chapter number 13, magnetic effects of electric current, and turn the page. See 13.2.3, magnetic field due to a current through a circular loop. And this is a magnetic field around a circular loop. By applying right-hand rule, we can find the direction of the magnetic field around a circular loop. And this is a very important point. The magnetic field lines in the same direction within the loop. So within the loop, the magnetic field directions are same. And this activity I explained. You have to read it, then you will understand. The next point, the next topic 13.2.4, magnetic field due to a current solenoid. So this is a definition for solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called solenoid. And this is a magnetic field around a solenoid. And see, for inside of the solenoid, the magnetic field lines are parallel to each other. And the strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside it. So it was shown this image. Here the soft iron is placed inside the solenoid. So the magnet so formed, such a magnet are called electromagnet. You have to answer for these two questions. And the next class we will see the 13.3, force on a current carrying conductor in a magnetic field.